but I can do mistakes if you, by your intuition, see that something is done better than on the key. Just follow it. So here's what we do on Friday. So please consider to submit these slides by Thursday midnight. So it is about I don't want to count, like 36 hours from now. We already have 2 submitted, which is like unbelievable. So here is a grading schedule. So if someone well, I noticed that those who sent by email all did number 6 perfectly. For me, it was the hardest. I think for you guys, it was the easiest one. Probably next year I should rebalance points. But if everything is done completely, then it will be 140%. So if something is, it sets up opportunity for everyone to stay in the A, even with some errors. And you just, for self-control, you see where your strong and weak places. So number 1, 10 points. So it's first one, just x squared. X is placed before and after, and one does see an example that it is not innocent. For the second time, one is placing the arbitrary function, and if this answer is received, just give full credit. At the end, I will ask everyone to add together the points. And if, while I'm talking, something is not clear, just raise hands. I'll tell, because I admit that I'm probably the worst calligrapher in the world, and maybe it's unreadable, and there could be some errors. So if no questions, let's go to the second one. Provide details for predicting future. So it's copy paste from the lecture. Just there should be time-dependent part, spatial part, and expansion coefficients, which are convolution of initial condition. So if you see it, just give full credit. Number 3, I will show it twice, because this morning I suddenly lost the portion of slides with key, and I decided that I'm hopeless and I need to redo it myself. So and I already looked some of you guys who did good try but made some errors. So someone I counted on made errors, and I just decided to check myself. So I will show first as I did it this morning, and then from previous years. So normalization. Wave function is normalization factor by the unnormalized wave function. Normalization squared times wave function squared should give 1, which means, so it's normalization square is not equal to this one, it's multiply. And then after we take the integral, one should, one is getting something, so n squared times something equals 1. And then to get n squares, one needs to divide 1 by this something, right? So one needs to find such normalization factor by multiplying which onto wave function, well, one will get 1. And then for taking the integral, there is a trick. So some of you did it naturally, some of you may have missed a factor. So we want to identify, so factor 2 comes here because we multiply wave function by conjugated. Then we want to change this everything in the power to y squared, which means our y square root of 2 times this separation. And then we can replace x by y over square root plus x naught. And if we replace derivatives, which also one not always can swap them 1 to 1, then derivative of y is square root of 2 of dx. Or dx is dy divided by square root of 2. And if this stuff is plugged in, then there is a Gaussian integral. Gaussian integral. Here's already letter y. which will give square root of pi. But in addition, there is a square root of 2 in the denominator because of this conversion of the derivatives. And then if n square is equal square root of pi over square root of 2, then n normalization factor will be square root of square root. And if one wants to plug it into the and then one can plug it and then one can plug it into the second part. So second part, with normalization factor square root of 2 square root of pi, we are taking the same integral, but now here is the x. So when one changes the variables, it's new. I made correctly or wrongly change of variables 2 times. It was easier for myself. Some of you may have done it in one step. So first, just shifted y as a x minus x naught, and then dx is the same as x dy. And here we replace x by y plus x naught, and we have minus 2y squared. So those are 2 integrals because they have different powers of the independent variable. One integral will be simply Gaussian with power of independent variable in front of exponential equals 0, and another power of independent variable in front of exponential equals 1. So you can call them I0, I1. So the one with the first power of independent variable in front of exponential, I can prove it graphically that it will be 0 because the exponential is even function, the y is odd function, and the result of integration from 0 to infinity and minus infinity will be equal by value, but opposite by sign. So this will be 0. And I0 with 0 power, we have this x naught up front. Then we do the substitution. Whatever is in the power will be our u squared. And then change of variables, dy will be du divided by square root, right? And then when we plug it in, it will be our factor from the normalization, square root of 2 by square root of pi. Then Gaussian integral, x naught. And then this 1 over square root of 2 due to change of variables. So we identify square root of pi. We have this factor, square root of 2 from change of variables. Everything cancels, and the answer is x naught. So, I believe I was declaring while announcing the homework the answer should be x naught. If some of you didn't get it, it should be ringing a bell. So if there is no answer x naught, withdraw credit substantially because it was already announced. It was a little strange not to find this. And then let's plan how to assign points. Maybe well, withdraw 15 points if the normalization is missing something. And withdraw points if the splitting, maybe withdraw 10 points if for second integral there is no splitting on 2. And also if you want to withdraw points if there are some minor errors that give factors. If one is getting answer x naught, multiply or divided by square root of pi or square root of 2, give partial credit because we all are humans and errors often come. Okay, so a little note. You see, it is doable by humans, but it's a lot of labor, and there is a chance to make error easily. This is a shortcoming of the Schrödinger approach to predict future. The goal is to find observable, and one can so easily get an error. In Heisenberg approach that we studied 2 days ago, the chances for errors much less, and it is a reason to have both methods on hands. Or opposite way is to practice Schrödinger approach, but with the computers rather than pen and paper math. Okay. To integrals. Now, number 4. If the right words are taught about that position and momentum cannot be measured simultaneously with any precision, just give full credit. Withdraw credits if the wording is strange, or I saw some of the words, but I cannot understand the logic, but some of you did show that uncertainty goes down. So it's maximal uncertainty at time 0, and then it gets more and more certain. So it's I saw a work with Gaussian function, just to show that it is not right approach. Withdraw at least half points. Okay. Number 5. I was counting that everyone will do it naturally, but this problem also gave a lot of room for errors. So let me tell by words before we go into details. This problem has multiple answers. So and it is a very typical situation in physical chemistry and quantum theory. So one equation has multiple answers, as when you draw orbitals, many energies, many orbitals. If someone of you get one answer, it immediately rings a bell. Something was not right. Not typical. So typically there should be a set of several solutions. Now, so we are finding solution in form of sine plus cosine, and we match the boundary conditions. If x equals 0, then sine turns into 0, cosine becomes into 1. So 0 plus b times 1 is b, right? But by our condition, this must be 0. So this gives us result that b equals 0, which means in what follows on the next page, we exclude cosine term completely. Make sense? Give me a little signature if it is questionable. Okay. Okay. So now after we agree that b equals 0, we will find solution in form of a times sine alpha x. So we already, by now we have only 2 independent things to find. So if x equals L, the unknown alpha times L, sine alpha L must be 0. We can imagine function of sine, and the function of sine will intersect x-axis multiple times, right? If the fringes are dense or sparse, it will intersect at different points. So the condition for sine equals 0 will be that argument in the brackets will be multiple of pi. 0, pi, 2 pi, minus pi, minus 2 pi, and so forth. Infinite number of solutions. So it multiple, which means unknown alpha times the size of the box times L should be natural number times pi, which means alpha should be any natural number times pi divided by L. Make sense? Everyone okay? No one, no protests. Okay, and then to find the A, one can practice normalization in the same way as we did a couple of problems ago. So wave function must be normalized. So this A times sine pi n over L times x. If we take it absolute value squared or conjugated and non-conjugated, a squared sine square blah 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 must be equal 1. And if one takes this integral, one will arrive that normalization factor is square root of 1 over L. So there are four unknowns. The alpha is most important. If the alpha is found correctly, give 15 points, even if everything else is wrong. And then for correct A, give another 10 and withdraw more if there are questions with if there are like if B is not equal to 0. And in any situation, put benefit on the doubt to the one whom you are grading, because we're just studying. It's not. Be gentle and generous. Okay. So number 6, I'm not providing key because this time it was extra credit. I will give it as a homework once again, and then I will probably give the, how to say, key. But it will be not forgotten. This this number 6 will be used in about 2 weeks. Everyone done? Anyone needs more time? Yes, I see. But so probably the one who is grading more than one work gets an extra credit for grading. Next time you can delegate this honor to someone else. So if you haven't done so, please add points together on the front page. It will make my life simpler. Okay, so I'm going to collect and keep it with me for until Monday, just to enjoy reading your works and grading, and then on Monday I'll distribute it back. Yeah, it's it should be divided, normalized, not to total number, not to 100, but divide by 100, so someone can get grades higher than 100%. It's a main idea for this extra credit thing. Really? Yes, there are some tough graders among us. Okay, yeah, thank you for this for cooperation in this thing, and I think we are progressing well towards the class. But a little observation is that even if we do effort so that we feel comfortable with points and grades, you see, those are really challenging problems. And one should be really like drinking coffee, be attentive to little points. So it's not my fault, it's fault of the course and the subject. And this is the reason why we do Wednesday labs and why you present MATLAB. So after soon we will balance between pen and paper solutions and some MATLAB exercises where there is a little less responsibility on human. One delegates part of it to the computer and gets some problems answered correctly without fearing of like one error discards 3 pages of derivation, which is sometimes discouraging. So and later on we will vote if anyone wants a true exam, but my preferred opportunity is that we all do project by the end of semester, and you come to idea that it will be a little easier than exam after doing this homeworks. Okay, so in some sense we have finished second chapter, and well, your presentations on Friday will be part of the second chapter, but we should slowly start the new one. So last time we proved that the center of the wave packet will move along the straight line, and you saw that it's no comparison of how easy are those equations and the one that you did in the homework. If you would like to find this answer of the linear motion directly by Schrödinger equation, it means right now in the homework in problem 3 you are doing x minus x naught for standing wave packet. If you do by Schrödinger, x naught will be not standing. It will accumulate position because of the phase factors. So one can get to the same result, but with much more efforts, longer derivations. And in this situation, Heisenberg is definitely like 20 times easier. Therefore, we need to have this toolbox in our arsenal. Okay. So I will start, okay, 20 minutes, just making general introductions to next chapter that we will seriously start on Monday, but so that the semester is brief, and I better use this few minutes to set our minds into right direction. So you already saw this picture, maybe in a little worse calligraphy. So we have evolution, Schrödinger, Heisenberg. We skip perturbation for future, and by now we did electron in a free space. So so it's electron that practices liberty and freedom. Now we will look at the electron that practices some chains, bounds, and pressure. So it will be electron in a box. So the electron in box, one-dimensional box, is the simplest problem in physical chemistry and quantum theory. And those of you who select academic teaching as your career will one day teach this subject for sure. In many courses, the free space is skipped because you already enjoyed the beauty of math. Particle in the box is easier and is less advanced in math, but more useful for practical reasons. So everything we study in chemistry typically has electrons confined to atoms or to molecules, right? We do not allow electrons to move freely where they want. They typically revolve around atom or are shared on the orbitals in the molecule between several atoms. And it's our goal to go there. But by now we consider very approximate constraint. So a molecule can be thought of as a region of space where electron is confined. And outside of this molecule, like there is a vacuum where it can move if we give it enough energy, but typically if the electron is not energized, it stays within the limits. And there are several practical applications where this simplified model works well on one hand, and on another, it is an ideal educational tool where all basic concepts of quantum theory can be practiced without too much math. So thank you for tolerating my ugly hand scratching for the semester. So this image should be, I do not like it. Sometimes in the news, one can see wonderful circus director taught an elephant to draw, and then shows like some arbitrary scratches. So I'm not very far from this drawing elephant, but let's try to see what is in this image. So there are cones directed downwards, several colorful cones, and they symbolize potential energy. So potential energy as ion attract electrons. So if you have a molecule constructed of several ions, in this very simplified drawing, it is like 4 ions. Each of them attract electron, and if electron is near the ion, its potential energy is more stable, it's lower. If it departs from the ion and from the molecule, it needs higher energy to do so. So very approximately, we can take the upper picture and consider it as a little box. So potential energy is minimal inside the molecule and maximal outside of the molecule. And the border of molecule is just a step function. So it may look too approximate, but it does work. I will show in which examples. And mathematically, it's quite simple. Well, nothing is simple, but it's much simpler than any true practical problems. No, those are just details of details about this attraction of electron by the ion. So I remember, it's not a joke, but it is a way to, how to say, improve the atmosphere of discussion. So let me ask, what is the political system in this country? How would you describe it? Okay. Which other political systems do you know from history or from looking at other countries? Monarchy, okay. So it's two poles: democracy when many people vote, monarchy when basically one person votes, right? Votes. Is there something in between? Like, for example, the time of the ancient Rome, when it was moving from republic to empire, and there was a transition period when not everyone was able to vote. And sometimes in modern history, it happens, and journalists start criticizing that there is a corruption, no freedom, only few people can influence the political system. So it's power, not everyone, not power of one, but power of few. So what's the name? Yes. Make sense? So now let's make connection to chemistry. Everyone is majoring in chemistry? Anyone in polymers and coatings? Okay, so let's look on the polyacetylene. So what's the name of this molecule? Come on, you should teach me chemistry. I need to admit, maybe I'll stop recording for a second. Okay, resume recording. Now teach me what ethane. Good. Now you are more brave that I didn't catch you telling something wrong. What is this one? Ethylene. So and we can made a molecule where this double and single bonds are alternating. So it's like ethylene, but this pattern of double bond repeats. What's the name of it? Polyacetylene. So then this one is monomer, this one is polymer. Like monarchy and democracy. What is in between? Huh? In between when there are few. So if it's not poly, not many, but few. So what would be the name? Oligarchy for political system and for polymers, for chemistry. Like monomer, polymer, oligomer. Okay, so it means polymer of the limited length. So if we build, like if the polymerization reaction doesn't go to its end, if we stop it, if we start polymerization reaction and then stop it in between, we will get chains that will have few monomeric units, right? And then it is exactly the situation that we discussed. There is a range along x-axis where electrons can move along this oligomeric chain, and there are ranges outside where electron cannot move or needs too much energy to play any role. So this oligomers of conjugated polymers are ideal examples of the particle in the box. And note that it is not any polymer. Here there are alternating single double conjugated bonds. So one can, in average, order of the bond is 1.5, right? And it should be interpreted that all double bonds at once can move, right? Which means moving electrons in space correspond to electric current. So in some sense, it correlates to your experience about free space, electron in free space. So they can move. If it is an infinite polymer, all electrons or one electron can move freely. So this alternating bond creates the option for electronic motion. And there was a Nobel Prize in chemistry, I think 2000 to 2001, for Hager and I don't remember other names, for the subject of conjugated polymers. And some people call them conjugated polymers, some people call them conducting polymers because they conduct electricity, and these carbonaceous materials can be used instead of electric wires, which is like a wonder. Typically we think of wires as something metal, and here one can synthesize them of the like byproducts of biodegradable stuff and like make computers out of carbon only. Not immediately, but in the future. So the oligomers of conjugated polymers is one of prey in our hand. So there is a range where electron is confined. It can move more or less freely in this range, and it can go outside. So outside is vacuum, inside is favorable playground. Here is another example of famous conjugated polymer. So it's you probably can give chemical naming better than myself. So benzene ring, when it's connected, it's phenyl something. And when there is this unit of the single and double, it should be something vinyl, same like siding on the buildings. You can check me later. So the name of this is polyphenylene, PPV. And it's quite easy to synthesize, and it also gives this opportunity to transfer current. And it's also another example when our oligarchy of polymers can be practiced. What else? Another, so here I'm telling a little bit more about chemistry, about examples. Another example is when one, what do you use? Not, maybe you do not, I do not use it as well, but what old people use to prevent wool in storage from insects? It's, I wouldn't say it's very stinky odor, but it's very specified. And sometimes I've heard jokes like if one smells this odor, it means an old man is coming. Huh? Naphthalene, right? So it's insecticide, and there are some insects that eat wool. If it stays in the storage for like 50 years, then insects will eat it. And if you put pieces of this naphthalene, it will stay. So it is when like benzene is one hexagonal ring. If one puts side by side two hexagonal rings, it will be naphthalene. And if one puts three, what would be the naming? Who took organic chemistry? One, almost ever. Who is taking organic chemistry or auditing it? So three benzene rings side by side. What's the name? There is a very similar name for mined coal. Anthracene? No? So there is an anthracene for the three benzene rings, and in biology there is a acceptor of electrons, anthraquinone, when it's connected with oxygens. Okay, but if one puts four, then it will be regular namings: tetracene, pentacene, and then polyacenes. So benzene rings on the side, it's another example of conjugated polymers. There is an area of organic photovoltaics and organic electronics when one tries to make circuits of these carbonaceous materials, leaving metals and semiconductors away. And another example is when one has 6-member ring with one carbon is replaced by sulfur. So anyone can help me from your organic chemistry namings? How would you call this? Huh? Yeah, perfect. Thank you, Adam. So thiophene. You should know it better, but when there is a sulfur, thio is typical for naming, like thio, right? Mercaptothiols with this stinky stuff in the natural gas that is added so that people find it. So polythiophene is one of the very popular conjugated polymer, and oligomers are also needed. Another example, and I plan to be more detailed, and on Monday we will seriously start the subject, but just to put seeds of thoughts to your minds. Suppose I hate organic chemistry because I do not remember namings, as we saw a minute ago. So it's, and then if I want to do material science, I need to return back to metals and semiconductors. It's either or. If I do not like organic, then I need to deal with them. And do electronics and photovoltaics on the solid materials, which maybe namings will be a little easier, but there will be other challenges. So what's the shape of, do you have your computers and you have your cell phones with you? What is the form factor of your devices? Are they spherical, cubic? Do they look like a stick? Or they look more like a pizza box? Just describe your devices. So they're flat. What is CPU? Did you hear this abbreviation? Exactly, or central processing unit. So did anyone intentionally or unintentionally broke a computer or cell phone and looked inside? So okay, how does CPU looks? Is it like a cubic or spherical or more flat? Flat. It's like flat stuff, depending on the generation. Sometimes it has cooling system, but it's mostly flat. So it's not frivolous decision. Everything is these form factors that engineers are practicing is affected by limitations of our technology. So the CPU is just a lot of transistors who allow current to go one or another way depending on the controlling current. And one needs to put as many transistors together to make this logic and help us to solve problems. So ideally, it would be really great to make them three-dimensional. Then it will be really, it will be like human brain is more like sphere, and it has high density of this neurons per like square centimeter, cubic centimeter. Computers are not as strong as humans because they're flat. And they're flat because there is no technology to make them three-dimensional. So the fabrication of computers works more like photograph. So one makes a blueprint, and then one projects it and makes like a drawing on a surface, making deposit, like either depositing or etching different materials, so that one deposits and etching like metal and different semiconductors, maybe then deposit another layer. But one cannot get more than a certain amount of layers. It will not stay. It will be mechanically breaking. So in anything that we use for our electronics and photovoltaics, the working horse of today are flat, how to say, regions of semiconductors, primarily silicon. And they are confined between substrate and another layers. So this drawing of BAB is an example when B can be like insulator, for example, glass or sand. A can be semiconductor, as for example, silicon, and B is another insulator. So it's not the computer. It's a very, very minuscule, small part. But by the way how things today are arranged, it is built of such thin things. Now, let's look on it. Oh, did you hear about competition of doing this like 30 nanometers processor, 18 nanometers processor, and next generation of Apple silicon will be something, they fight for 3 nanometer CPU technology. Do you hear this nanometers? No? So there are like advertisements and bragging between computer companies about, they brag about size, amount of transistors, and size. Size, not the processor itself, but elementary unit. So the size in this direction between two insulators, how small is this element, is what they measure in nanometers, and the thinner they can do it, the better. Now, from the point of view of physical chemistry, in this direction, pizza box is quite big. We don't care. And in this direction, it is confined, constrained. So the electron, if you inject it, can move in silicon atoms here forwards, then it is reflected from this insulator, because insulators do not accept electrons, and then it goes back. So it will be electron going forth and back. And this will be another example of the particle in the box. So electron in the semiconductor constrained by layers of insulator. So you may criticize inside yourself like, box, so simple. It's no relation to real molecules, but it helps to do technology with very, very simple approaches. And this, even one can publish papers based on the particle in the box model, although it looks ridiculously simple, and everyone was able to solve this problem since maybe 1926, from like first day Schrödinger equation was announced. So it's one of the simplest problems. I think I'm over time, but basically let's continue on Monday. I'll show more pictures and explain what they are, and see you tonight in the lab, and looking forward to see your slides tomorrow night, and looking forward to hear your talks on Friday morning. Whew, meeting is done. Sorry for speaking a little longer, and I'll stay here if any questions appear.
I might not be able to make the lab tonight.
Huh?
I might not be able to make the lab tonight.
That's fine. That's fine.
If I just watch it.
Sure. Yep.
All right. Thanks.
Yeah. Thank you.